Welcome to the deep dive. Today, we're really getting into one of those classic RC frustrations. If you, the listener, have ever had your hands on a Tamiya Grasshopper or maybe a Hornet, you know the feeling. You're running it, hit a bump, maybe land a small jump, and suddenly just that high-pitched motor whine, no movement, the dreaded axle pop out, it just stops the fun cold, doesn't
Yeah,
it?
absolutely. It's like a rite of passage for owners of those kits. For years, people sort of accepted it. That's just how those old gearboxes are.
Right, part of the charm maybe? Or just a pain?
Maybe a bit of both.
Mm-hmm.
But today, we're not just complaining about it. We're treating this as a fascinating little engineering case study.
Yeah.
We want to go beyond that surface-level frustration and really understand the why. It's this interplay between, like, the 80s design thinking, the manufacturing limits of the time, and just basic physics.
I like that approach. So uncover the root cause.
Exactly, and then reveal the fix, which is surprisingly simple but elegant. How a tiny, cheap part basically re-engineers the whole setup.
Okay. Because fundamentally, these Tamiya designs, they're simple, they're robust, they were meant to be easy to build, take a beating.
They really were a masterclass in that respect.
Hmm.
Affordable, fun, almost indestructible in some ways.
But you're saying that simplicity itself kind of baked in this weakness, this potential for failure.
Precisely. The elegance hides a vulnerability that's just waiting for a little bit of looseness, a bit of slop, to cause problems.
So to get to the bottom of this axle pop-out, where do we start? The suspension.
Yeah, you have to start with the architecture, that unique, rolling, rigid axle rear suspension. It's quite different from modern designs.
Right. It's not independent suspension.
Sure.
The motor, the gearbox casing, the axles, it's all one big lump back there.
One heavy lump, yeah. And that whole unit just pivots on 2 points connected to the main chassis. It hinges up and down.
Simple, definitely. Easy assembly.
Super simple. But that design choice has a huge mechanical consequence. Massive unsprung mass.
Unsprung mass. Okay, explain that. That's all the weight the springs don't support directly.
Exactly. It's the weight that has to physically move up and down every single time the wheel hits a bump or a dip. So wheels, tires.
But here, it's also that entire heavy motor and gearbox assembly that's all unsprung.
Correct. And when you have that much unsprung mass, the suspension just can't react quickly or smoothly. It's like trying to dance with boots full of lead.
Okay, I can picture that. It leads to that kind of bouncy, almost pogo stick ride those buggies are famous for, that boingy feeling.
That's it, exactly. The suspension gets overwhelmed. Instead of soaking up bumps, the whole heavy rear end gets slammed around. And here's the crucial part. That violent movement, those impacts, they send shockwaves and vibrations directly into the gearbox internals.
Ah, so the external forces from just driving around are actively trying to shake the differential apart from the inside?
Pretty much, yeah.
Yeah.
Especially if there's any internal looseness already present. Which brings us to the heart of the matter. The differential itself.
Inside that plastic two-piece gearbox shell, the B parts. The simple three-bevel gear differential.
The simplest diff design, really. You've got the main spur gear bringing power in. Inside its carrier are 3 small bevel gears. People call them spider gears.
Right. And then the 2 larger side gears slide in from either side, and those are what the axle shafts actually connect to, with splines.
Correct. And the whole thing only works, the whole power transfer relies on those 2 side gears staying pressed firmly against those 3 little spider gears in the middle.
So if those side gears move sideways, axially, even a tiny bit, the mesh is gone.
The whole geometry falls apart. The spider gears can just pop right out of their little pockets. Which leads us directly to the root cause, slop, or more technically, tolerance stack-up.
Tolerance stack-up. Okay. And this wasn't necessarily a mistake in the design?
Not really a mistake, no. It's more like an intersection of the design goals of the 80s and the realities of manufacturing back then.
Tamiya wanted something durable, fun, easy to build, right? Not necessarily a super precise racing machine with a zero play.
Exactly. And arguably, a little bit of give or flexibility in a plastic assembly like that might have even been seen as a benefit. A system that's too rigid can sometimes just snap under impact.
So a bit of flex was maybe okay, even intended.
Possibly. But that design philosophy meets the hard reality of manufacturing tolerances. No part is ever perfectly the exact specified size. There's always a tiny, permissible variation.
Okay, let's unpack this tolerance stack-up idea properly. It's like building with slightly uneven bricks.
That's a great analogy. Each part the gearbox halves, the seats where the bearings or bushings sit, the thickness of the gears themselves, the diff carrier width, Each has a small allowed plus made variation.
And stack up means all those tiny variations can add up.
Right. If you happen to get a set of parts where several of these dimensions are on the loose side of their tolerance range, the small gaps accumulate, and they create one larger, noticeable gap, or slop. Specifically, in the crucial spot between the interface of the axle bearing or bushing and the outer face of that differential side gear.
Ah, so there's physical empty space there, allowing sideways movement.
Precisely. Space for the axle shaft and the side gear attached to it to physically shift inward towards the center of the diff.
And that specific slop is the fuse for the whole catastrophic failure chain, especially with those big suspension hits we talked about.
Exactly. That violent suspension movement causes something engineers sometimes call pivot slap.
Pivot slap. Okay, let's nail that down. What is it?
Imagine the buggy lands hard after a jump. That heavy rear axle assembly slams down, right? When it hits the limit of its downward travel, often hitting the chassis or suspension stops, that sudden deceleration sends a shock wave through the whole assembly.
Okay.
And because it's a pivoting system, that force isn't just vertical. It creates a momentary stress that tries to push the axle shafts inward towards each other, towards the differential center.
Wow. So the impact is literally trying to shorten the axle assembly.
For a split second, yes.
Yeah.
And that inward force immediately takes advantage of any slop created by that tolerance stack-up,
So the axle moves inward.
pushing the side gear inward with it. And because that simple three-bevel diff has nothing else holding those little spider gears in place except the pressure from the side gears.
Moving the side gear lets a spider gear lose mesh and just pop out.
Pop. Right out of his pocket in the spur gear carrier.
And boom, instant freewheeling, no power.
Complete loss of drive. It's amazing how that simple setup works perfectly until that axial slop allows that tiny bit of movement.
Modern diffs don't have this issue because they usually have a cross pin holding the spider gears, right? Inside a sealed case.
Exactly. They mechanically capture the spider gear, so even if the axles have some side-to-side play, the diff internals stay put. The Tamiya design's beautiful simplicity is also its Achilles heel here.
Okay, so I've got a clear diagnosis.
Right.
Tolerant stack-up creates slop, pivot slap provides the force, and the simple diff design provides the failure mechanism.
Like perfect storm, really.
Yeah.
But the solution, this is the best part. It's not some complex redesign. It's incredibly simple.
Don't keep us in suspense.
It's a shim, a thin precision washer.
A shim. That's it. It seems almost too simple for a problem that's frustrated people for decades.
It does sound anticlimactic, doesn't it?
Yeah.
But shims are fundamental tools in precision mechanics. Their whole job is to take up unwanted space and precisely control the axial position, the end-to-end location of rotating parts.
Okay, so where does this magic shim go?
You use standard 5mm inner diameter shims, because that's the axle diameter, and you place them inside the gearbox. The critical spot is between the inner race of the axle bearing, or plastic bushing if you still have those, and the outer face of the differential side gear.
Right in that gap where the tolerance stack-up created the slop.
Exactly. You are physically filling that empty space. The shim prevents the axle and the side gear from moving laterally inward.
So it just blocks the movement that lets the spider gear pop out.
It does more than just block it. It fundamentally changes the nature of the assembly. The stock setup with slop is kind of a dynamic floating system where things can shift around. Adding the right shim transforms it into a static, constrained system. The axial position of the side gear is now fixed, locked in place relative to the bearing. It's reliable.
Okay, so primary benefit. No more axle pop out. Huge win. Are there secondary benefits? Does making it more precise actually improve performance?
Oh, absolutely. This is where it gets really good for the enthusiast. By eliminating that slop, you force the gear teeth, the side gear meshing with the spider gears, and the spiders meshing with each other to engage at their design depth. You get full face contact.
Ah, instead of maybe just the tips of the teeth hitting each other if things are loose?
Precisely. Partial contact concentrates all the force on a small area, which causes rapid wear, creates more friction, and wastes power. Full face contact distributes the load properly.
So less wear on those vintage gears.
Much less wear, meaning longer life for the drivetrain parts.
And better efficiency.
Yeah.
Smoother running.
Definitely smoother and more efficient. You're eliminating that lash or play in the gears. It often makes the gearbox noticeably quieter, too. Less friction means more power gets to the wheels and smoother response.
Quieter is always nice. You're essentially blueprinting the gearbox like engine builders do, bringing it up to a higher standard of precision.
That's a good way to put it. You're using a simple tool to achieve the precision the original mass production couldn't consistently guarantee.
Okay, let's get practical. If someone listening, our learner, wants to do this, what's the actual process? It
Got
sounds like you can't just slap any old shim in there.
No, absolutely not. This requires a bit of care. It's an iterative process. You need a selection of 5 mm ID shims in various thicknesses, usually 0.1 millimeter, 0.2 millimeters, and 0.3 millimeters covers it.
Why the different sizes?
Because every gearbox is slightly different due to that tolerance stack-up. You need to find the exact thickness needed for your specific gearbox. You start by assembling the diff, maybe without grease first, just to feel things out. Try putting, say, a 0.2 milliliter shim on one axle between the bearing and the side gear. Close up the gearbox temporarily. Now, try to push and pull the axle shaft in and out. Can you feel any side-to-side movement, any click or clunk?
If there's still movement, add more shim.
Right. Maybe try adding a 0.1 millimeter shim, making a 0.3 millimeter total on that side, or maybe the other side needs one. You repeat this, adding shim thickness incrementally.
Until all the sideways slop is gone.
Exactly. But here's the crucial countercheck. You must ensure there's no binding.
Binding, meaning it's too tight.
Yes. Once you think you've removed the slop, spin the axle by hand. It must spin completely freely, with no noticeable drag or tightness.
Ah, so if you feel resistance, you've added too much shim.
Correct. Too much shim compresses the gears together, creating friction, heat, and rapid wear. That's just as bad as having slop. The goal is 0 axial play and 0 binding. Perfect free rotation.
So it might take a bit of trial and error, maybe a 0.2 millimeter on one side and a 0.3 millimeter on the other.
Very possibly. You might need different thicknesses on each side to perfectly center the differential assembly within the gearbox housing while removing all play. Patience and feel are key.
That makes sense. Precision work. Now, since the gearbox is open anyway, are there other things you'd recommend doing at the same time? Complementary upgrades.
Definitely. 2 things really work hand in hand with shimming, based on sort of a drivetrain troubleshooting matrix approach. First is upgrading to ball bearings.
Getting rid of the stock plastic bushings.
Exactly. Those plastic bushings, even when new, have significant radial play that's wobbled, side-to-side rocking of the axle shaft.
Which probably makes it harder to accurately shim the axial play, right? If the axle itself is wobbling.
Precisely. Ball bearings provide a much more stable, true spinning axis for the axle. They eliminate the radial play.
So bearings handle the wobble, shims handle the in-out movement, they work together.
Perfect combination.
Sure.
Plus, bearings reduce friction dramatically, which means a bit more speed and longer run times. Win-win.
Okay, what's the second thing?
The anti-slap mod we touched on earlier. This addresses the source of those harsh impacts, the pivot slap.
Right, trying to reduce the violence of the suspension bottoming out.
Yeah. People do this in various ways, adding pieces of rubber fuel tubing to the shock shafts or limiting straps, basically anything that gently restricts the maximum upward travel of that heavy rear pod relative to the chassis.
So shimming fixes the gearbox's vulnerability to the shock.
And the anti-slap mod reduces the severity of the shock itself. Doing both gives you a really robust and smooth drivetrain.
Okay, this paints a much clearer picture. We started with what seems like just a simple, annoying flaw, the axle popping out. But we've found it's really a fascinating story about 1980s design choices, manufacturing limitations, and basic physics. It wasn't just a mistake.
It really wasn't. It was a consequence of prioritizing simplicity and cost, which led to a design sensitive to tolerance stack-up, activated by the forces inherent in its own suspension geometry.
But the solution, that tiny shim, shows how a little bit of precision thinking can make a huge difference.
It's incredibly satisfying. By understanding tolerance and using a simple shim to control the axial position, you, the hobbyist, are essentially finishing the engineering process. You're applying modern precision to optimize a classic design.
Allowing it to perform better than ever while keeping that vintage charm.
Exactly. You get to appreciate the original elegant simplicity even more because you've addressed its one key weakness.
So the final thought for you, the listener, to maybe mull over. This deep dive focused on one specific vintage RC issue. But think about it. How many other beloved vintage designs, old cars, classic hi-fi gear, maybe early computers are held back not by a fundamental design flaw, but simply by the accumulated slop from the manufacturing tolerances of their era?
That's a great question.
And what other simple, maybe overlooked precision fixes like our little 5-cent shim are just waiting out there to unlock hidden performance, improve reliability, and let us appreciate those classic designs even more today? Makes you look at old tech in a new light, doesn't it?